Oh, hey, Pete.
Do I need something?
Is this it?
No, it's a real thing. Look.
There's a book under here. Is it?
It's a PCR thing.
I don't see anything.
Ha.
You're fine, Reed. Look at your slinking.
I want to be quiet.
Okay. Officially noon. I guess I have to start class. Kind of nice having Monday off. But I'm so adult now. I did stuff like laundry, you know.
By the lawn.
I don't have a lawn. I got some weeds.
Yeah.
I sprayed it with Roundup last week. I don't know. It's my version of mowing the lawn, watching it die. But yeah. So does anybody have any questions about anything before we start? So, I mean, we've got, I think, 6 classes left, and we'll probably finish this stuff in 3 or 4. So we'll have lots of time to review for the final, which is nice. So I'll probably switch to an Emporium kind of model where we do problems. So, and today, I remember talking to, when I was teaching at UH Manoa, where I was talking to the chair. He's like, oh, what are you covering today? And I was like, oh, I'm covering Vesper. It's like, time to tell the students more lies. And we chuckled in the inside joke because this is actually wrong. So what I'm about to teach you is incorrect. Lewis theory, also incorrect. So the real reason why things bond is because of the collection of nuclei and electrons when they come together. If they can form a more stable configuration than them being apart, then they'll bond. So, and that has to do with some high-level physics, mostly electricity and magnetism combined with quantum mechanics. So that's the real reason why things bond. And it so happens that very commonly it follows the octet rule. So, and it aligns almost perfectly with Lewis theory, aligns almost perfectly with this theory here, but there are some things that are, some fine points that make it wrong. So back in the 1970s, VSEPR and some other theories we'll talk about were in competition with molecular orbital theory and the emergence of quantum mechanics. Well, I guess quantum mechanics was around the 40s and 50s when it emerged, but it was being developed. And it turned out that quantum and molecular orbital theory is right, and VSEPR was wrong. And it's kind of like, I don't know if you follow scientific theories, it's kind of like quantum mechanics versus string theory right now. So string theory is not a scientifically valid theory because it aligns almost perfectly with quantum mechanics, but there are some things that are wrong. And there's also more than one string theory. So it's not like string theory is one thing. There are several different string theories. Which one is right? It's very mathematically complex. And the math is really weird, too, in string theory. It's really kind of wonky. They have like limits on things that don't make, to me, that are divergent and don't make sense. But they apply in string theory. And mathematically speaking, it's a fuzzy area because it's a divergent series, but you're forcing it to appear something that breaks some mathematical rules, but that's a difference. That's above and beyond this class. But that's like kind of scientific dueling going on right now. Who knows who's going to be the winner? But this was going on in the 70s, and VSEPR was a clear loser. But so why am I teaching it? If it's wrong, why am I teaching it? It's because it's still very useful. And people were bummed. People were really bummed when they found out this was wrong because it makes so much sense. It is so. It's like I said. It makes sense. You're like, oh, this. I can see this in my own life. So let me say this out. VSEPR, sometimes called VESPER. So if you hear something VESPER. Valence shell electron pair repulsion. So the idea here, so valence shell, outside shells of electrons, so outside electrons, outer electrons, and these outer electrons repel, and then that forms geometries. So, this mostly works. Oh, I should back up. Also, what the other thing that research is going on right now about stability of compounds, it's also what it's dissolved in. So that's kind of the novel research right now. We are seeing that what things are being dissolved in change the types of compounds that can be formed. That has applications in astrochemistry and in life, because there are certain molecules that will not form in space. They can only form in a liquid phase, for instance. And that's important because certain molecules are needed for life. So life as we know it could not be created in outer space, from what we understand now. You specifically need to have a liquid phase, something like water, to have that happen. So, but it's an emerging field and it's beyond this course. But I like to talk about some things like that because so you can see where we're going in science. But science is ever changing. Okay, so valence shell electron pair repulsion. So let's start with the simplest thing, 2. So you have a central atom. Well, actually, I should say the simplest is probably 2 without a central atom. If you have 2 things, it's going to be linear. So can you take 2 points, so like 2 fists? Can I make any arrangement? And linear means a line can go through it. Can you describe 2 points and anything that they wouldn't be in the same line? And the answer is no. 2 points define a line. So when you have 2 points, they define a line. So now let's go to 3 things. And if we have 3 things and a central atom and 2 bonding groups or 2 electron groups, so see the beryllium atom here as a center and see the 2 chlorines as just big balls of negative charge. So these are big regions of negative charge because the electrons, that's basically what atoms are. If you are something approaching an atom, what does the atom look like? It looks like this big region of negative charge, and that's the electron cloud. So you have these 2 big regions of negative charge attached to a central beryllium atom, and what happens is, so imagine beryllium here, chlorine, chlorine. So and the idea is these electron clouds, they want to be as far away from each other as possible. So be as far away as possible. So what form are they going to form? Or what's the structure? Linear. So these chlorines are going to be all collinear with the beryllium center. So let's say we move it here, like, oh, I want to get away from the repulsion back here, so I'm not that flexible going that way. So go here, but the problem is now they repel this way. So if they go, I'm not very flexible this way, here they start to repel that way. And so they just go straight linear. So 2 things, 2 bonding groups and a central group form a line, kind of like if you are in some sort of cosmic dance club where you have something in the center that you have 2 parties that are interested in the center but are extremely repelled by each other. And with my student evals, I should say, excuse my heteronormality in this. I'm just trying to illustrate a point. What is going to happen in this circumstance? They're going to form a line. That's why they can be as far away from each other as possible because they're utterly repelled, but they're attracted to something in the center, so they're going to be as close to that as possible. So what's going to happen if number 3 wants to join in this? So what's going to happen? I should say and we can have more than single bonds. You have double bonds. We'll talk about bonding later. If you have three things that approach each other, they form a triangle. And so now let's talk about just simple geometry. So talking about simple geometry, right? So two points will define a line, and now we have 3 points, and they're all collinear. So these two molecules, these are linear, which means this is different than another geometry. So this is linear. If it's skewed, this is known as bent. So we'll talk about bent later. But for two big electron groups, it forms linear geometry. And if a third group comes in the mix, then there is coplanar geometry. So 3 points define a plane. Just like 2 points define a line, 3 points define a plane unless the 3 points are collinear. So if you have, I can illustrate with this. So flat sheet, this is a plane. Okay, this is a plane. And a line, so like this edge here, this is a line. So if you have 3 points on that line, you can define an infinite number of planes. It just slices through that line. Okay? So, but if you have 3 points that are not collinear, so 1, 2, 3, those 3 points define a plane. And you might know this because your seats that you're on, they have 4. Have you ever noticed that sometimes your chairs are not completely balanced? And you like lean back, and it's like, oh, it goes one leg, oh, it goes the other. One leg, other. The plane here is the floor, but only 3 points. So if the 4 stubs on your whatever, the 4 legs on your chair are not, if they're not coplanar, you will go back and forth between 3 of them, but the 3 have to be coplanar. So that is Euclidean geometry. So the Greek mathematician, philosopher Euclid. Euclidean geometry, 2 points define a line, 3 points define a plane. And so for 3 electron groups, they all are coplanar. So meaning you can take boron trifluoride and you could slice a paper, like I said, if you have a piece of paper, you could slice through all of the nuclei. They will all be coplanar. And later on, we'll talk about pyramidal structures. You can have 3 of them, but then instead of being coplanar, they can be kind of like this, where you have the center one and the 3 on the bottom. Ammonia is like that. So you can have a pyramidal structure. And coplanar, so this is, just flat. The molecule will be flat. So these molecules are flat. They're coplanar. And notice each of the fluorines here, it's the same atom. So this electron group, they're all the same electron groups. And with all the same electron groups, you have the angle between each of these be 120 degrees. So that's 360. 360 defines a circle. I'm assuming do you guys like degrees better, or do you like radians? This will be 2 pi over 3 radians. Some students like radian. I guess some people listening online. So the radians, this is 120 degrees, which is 360 divided by 3, or 2 pi over 3 radians. So a circle is 2 pi radian angles divided by 3. Now, let's change, these are all the same, so they're all completely even. Let's change an atom. So this is formaldehyde. This is formaldehyde, and with formaldehyde, you have this oxygen here. What that oxygen has, and this is Lewis theory, but it's still valid. Did my thing go to sleep? My Apple Pencil's not wanting to work now. Okay. Technical difficulties. Did you wake up? There we go. It woke up. All right, so the oxygen atom has 2 lone pairs. But either way, there's this really large negative charge here. So the valence shell electron pair repulsion. This is the valence shell. There's this huge electron cloud here, and it's very negative. So what happens is now here are the hydrogens. They're like, oh, this is my 120 degrees, 2 pi over 3 radians. This is really comfortable. my third arm behind me is oxygen. It gets really big. It's really big and negative. And what happens? It scoots these hydrogens forward a little bit. So it's not the perfect 120 degrees. It bends the angles a little bit forward. So that's the pair repulsion. It's pushing it forward. So VSEPR would predict this angle to be smaller. And that is correct. This angle, the angle here between the hydrogens, is in fact skewed more tightly because of that electron pair repulsion from that oxygen atom. These are all still coplanar. These are all coplanar, but it's not the perfect 120 degrees. It's slightly askewed. And the reason for that is because the electron groups are negative, and they try to be as far away from the other negative groups as they can. Is this making sense? Okay. So now, I mean, in the chemistry dance floor, and I'm getting partially chemistry dance floor from a video. I guess I can show the video. This is kind of fun. This is a European video. It'll probably be, yeah, here we go.
Our pets
Oh,
are just
come
like
on.
us. Why would we feed them any differently? Wholehearted, exclusively at Petco.
So here's the European dance party.
Can't get it now.
So
Can't get it now, but I can get
the
it.
carbon coming up.
Can't get it
Oh, here we
now.
go.
I can't get it now, but I can get it. Walk up the stairs. Walk up the stairs. Can't get it now. I can't get it now. I can't get it now.
And notice the third guy went in a different structure. So the three were up top and the one is below. And I hope I'm not offending anybody by any of this. But that's, so I said the chemistry dance party. Where's my thing? So instead of three, it forms four. But where we dance floor is coplanar. Atoms exist in 3D space. Therefore, instead of a square, it forms a tetrahedron. So because we have it's not just the plane, you can go above the plane in 3Ds, in three dimensions. So four groups, so two groups, linear, three groups, coplanar, four groups, tetrahedral. So the tetrahedron can form with the four groups, and the idealized, I don't know this is what it is in radians, but the idealized structure for a tetrahedron is 109.5 degrees. So whatever that is in radians. So, here, so you might also see this molecule written. So this is methane. This and this mean the same thing. This is known as a Fisher diagram. So these two here, these hydrogens are like this, and these two here are like this. So it's like two V's. Again, my fingers are not very flexible like this, but it's like two V's coming together like this. And then the idea is these are popping out at you, and these are pushing into the paper. So you can kind of visualize things in a three-dimensional way. So this is what and this is the ball and stick model. So this and this are the same thing, but this is just printed on a piece of paper. Of course, nowadays, technology is better, so we can actually make things 3D, if we want to. Like I've got 3D stuff on my iPad. But here is the tetrahedron, and if you have four groups that are all the same, you will have this idealized bond angle. So let's replace that with something else. So here is ammonia. So ammonia's Lewis structure is like this. And ammonia, so the electron groups, so the electron groups, and there's 4 groups. So that's number 4. So methane, CH4, has 4 groups. They're all hydrogens. They're all bonding groups. So ammonia has 4 groups. It has a hydrogen, a hydrogen, a hydrogen. So 3 bonding and 1 non-bonding. So it has that 1 electron group that's non-bonding. And what happens is, so the idea here is this lone pair, this doesn't have an atom to it, so it gets to be a very, very large ball of negative charge. And where you have that idealized angle, so the idealized tetrahedral angle is 109.5, and you have that huge amount of electron pair repulsion, what happens? That bond scoots in. So this group back here will cause the 3 prongs of the tetrahedron to scoot in. If you can see my fingers, I'm dramatizing. It's only like a 2.5 degree difference, but it scoots in, like goes in that way. Because the electron clouds of the hydrogens don't like this really big diffuse electron cloud, they're moving away from it. So, and then this structure, this is pyramidal. So this is known as a trigonal, trigonal pyramidal. So 3 base. So like the pyramids in Egypt. I've never been to Egypt. I've never been to Africa. Oh, here we go. I drew them. So the pyramids in Egypt, it's a 4. Man, my pen's not working. Maybe I need to charge it up. I guess well, here's the pyramids in Egypt, and they're square-based. It's a square-based pyramid. And we do have molecules that have square-based pyramids. But the pyramidal structure for ammonia is a triangular-based pyramid. So, have this way, so it's trigonal pyramidal. And as you go up in the number, so this is also simple geometry, if you go from triangle pyramid to square pyramid to pentagonal pyramid on up, an infinite number is a cone. So if you have an infinite number of points, you have a circle. And a circle pyramid is also known as a cone. So you have a circle base, and then you have a point, and then it's a smooth top all the way up. So the limit, if you want to go limits, the limits of that, as you add more atoms around, that would be a cone. Okay, so we have the tetrahedron, methane here, 4 bonding groups, 4 groups all bonding, tetrahedral electronic structure, tetrahedral geometric structure. We have ammonia, we have 3 bonding, 1 non-bonding, 1 lone pair, so 4 groups. The electronic structure is tetrahedral, so, and the molecular structure, just the atoms, it's pyramidal. And now we're going to go one more to water. Water has 4 groups. So here's the Lewis structure for water. We have 2 hydrogens, so 2 bonding groups and 2 lone pairs. That's 4 groups, 4 things around it. And so that means the electronic group is tetrahedral. And then if you just look at the atoms, the bonds, the bonding groups, it is known as bent. So, and the same idea with the valence shell electron pair repulsion. So 109.5, that's the idealized tetrahedron. What happens to water? It has those 2 big clouds of electron groups. Scoots in. It scoots in a little bit to account for that big amount of negative charge back there. So are you guys following? Any questions? Okay, so, and I keep on mentioning what is this electronic structure? Why do I keep on talking about that? Later on, we're going to talk about hybridization. And hybridization, for linear groups, the hybridization is sp. For planar, it's sp2. For tetrahedral, it's sp3. So we'll talk about that, not this class, it'll be a future class, but I'm trying to let you know that's where I'm going with this. I'm talking about, and that has to do with the electronic geometry, not the molecular geometry. The molecular geometry deals with the atoms, but the electronic geometry deals with the atoms and the non-bonding groups. And to show you VSEPR, valence shell electron pair repulsion, having the more negative groups pushes those bond angles in. So the more negative groups will push the bond angles. Okay. How are we doing? Questions? So what about 5 things? So we talked about 4 things. Now, if you remember, we talked about expanded octets. So expanded octets can only deal with when you're in period 3 and above. So period 2, and much of our bonding deals with period 2. So, because most molecules that we deal with contain carbon, hydrogen, oxygen, nitrogen. So CHON. That's the vast majority of the molecules that we know just contain those 4 elements, and that's mostly what we are made of. We are vastly made of. By atom, we're mostly hydrogen. By mass, we're mostly oxygen, and that's not surprising because we're about half water, right? So H2O. But we are our molecules and what's in our molecules and our structure is mostly carbon. So our backbones for all our molecules is carbon. So and nitrogen is found in proteins. So amino acids, amine means nitrogen. So we have quite a bit of nitrogen in us too. So, but we are, like I said, mostly by atom, we're mostly hydrogen. By mass, we're mostly oxygen. And the next biggest number is carbon. And then after that is nitrogen. After that, it's phosphorus and iron, if you want to know, because there's phosphate groups in there. And our adenosine triphosphate, so phosphate, phosphorus, our phospholipid bilayers in our cell membranes. Hydroxyapatite has phosphorus in it too, and our DNA has phosphate groups alongside the chain. So we have quite a bit of phosphorus. But everything else is mostly carbon, hydrogen, oxygen, nitrogen. So that's only going to go up to tetrahedral. So all those structure is going to be linear, coplanar, and tetrahedral. So when we go up higher, though, so phosphorus it doesn't do this in phosphate, but phosphorus for inorganic molecules can go up to, can bond with 5 things. So here is phosphorus pentachloride, and phosphorus pentachloride has what's known as a trigonal or trigonal, however you want to pronounce it. I usually say trigonal bipyramidal geometry. So the idea is that there's these 3 atoms. These are all coplanar. So those 3 atoms are known as the equator. So imagine here, and I'm kind of naturally putting around my center of mass. So there is the equator here. So, and that means that if my center of mass here is the phosphorus, I have a chlorine here, a chlorine here, and a chlorine here. And then there's above and below. This is known as the axial, the axis. There's a chlorine here in my head, and then another chlorine by my knees, kind of thing. So, right. So this is the axis. That's the axis. This is the equator, the equatorial plane, and this is a plane. That's an equatorial plane. And so here, phosphorus pentachloride, 5 things, all bonding groups. The electronic structure is trigonal bipyramidal. I usually just call it, now I'll probably say bipyramidal from here on out. So bipyramidal electronic geometry. So molecular geometry where the atoms are, bipyramidal. So why am I making this distinction between electronic geometry and now I'm putting another focus on molecular geometry? So the electronic geometry is going to be important for the hybridization. And organic chemistry really heavily relies on this. So the hybridization is important for organic chemistry. And then the molecular geometry, this is important for deciding if a molecule is polar or nonpolar. So we're going to talk about molecules if they're polar or nonpolar later. And that's directly tied into the molecular geometry. So that's why I keep on making this distinction. So okay, let's. This thing does not work. Have to mime this, I guess. So the next thing we're going to look at is we're going to put a lone pair somewhere. Where do you think? Do you think the lone pair is going to go in the equator, or do you think it's going to go in the axis? That no one wants to play. So the bond angle of the equator is 120 degrees. The bond angle of the axis is 90 degrees. This is not as intuitive to me. So here's the equator along here. Here's the axis. If you put an electron group, so imagine me with a big head, the electron, this big negative charge here, if you have the electron group on the axis, it puts it closer to these at 120 degrees. So it's 90 degrees. So that's also, if you have a plane and you have something that's perpendicular, so if you have a plane and you have a line that's perpendicular to that plane, it is perpendicular at all points to the plane. So that's another geometric theorem. So if you have a plane and you have a bisecting line of the plane, if that's perpendicular to that, it is perpendicular from any angle. So if I have, so if you imagine this line here, imagine that instead of, here's the plane, and here's a line going here. It's perpendicular here, but it's also here, here, and if this is just a line back here, every single, along a circle, it's perpendicular alongside each of those lines. So yeah, just like the pencil through your hand. That's a better visual. Thanks, Reed. So this pencil through the plane is perpendicular at every angle. Okay, so if you have, luckily someone left some fruit here. So if you have a big electron group here, it is it is 90 degrees to this other group. Okay? If it's 90 degrees there, but what it actually prefers is for it to be on the equator, because now it's 120 degrees. So when you get big electron groups, they're going to populate the equatorial positions before the axial. And what's different, so this is also what's different about the bipyramidal geometry. Every spot is equivalent. So linear, having it be on this end or the other end, it doesn't matter. It's the same. Coplanar, it doesn't matter which one of the three you're in. It's all the same. Same thing with tetrahedral. They're all the same. This is where we start off like, oh, these are not the same. So now there's going to be a difference between the two. So, okay, so when you have a big electron group, it tends to go to the equator. And an example like this is, so that's sulfur tetrafluoride, so SF4. It's hard to see on this one. That's sulfur tetrafluoride. That large electron group goes along the equator. So now we have 5 things, 4 bonding, 1 non-bonding, still 5 things. The electronic geometry is bipyramidal. The molecular geometry is now known as a seesaw. So you ever do this when you were a kid? I remember playing on seesaws where you have, looks like a wedge, and then you have the going up on that. That's what we have here. We have the wedge. You have the wedge, and then you have the other one, and it's just like the seesaw that you were playing on when you were a kid. So the seesaw geometry. So that's molecular geometry. And what about, now we're going to add another electron group. So bromine trifluoride. So bromine trifluoride has 2 lone pairs. And as discussed, the big electron groups go on the equator. So we have 2 electron groups, 2 lone pairs on the equator, a bonding group on the equator, and 2 bonding groups on the axial positions. So the electronic structure is still bipyramidal because we have 5 things. And then sometimes the 5 things, sometimes that's called the steric number. That's just the number of things around something. Now then if you ignore the lone pairs and you look at the molecular geometry, you have this structure, and this is known as T-shaped. So you can see we have these really complicated names in chemistry, right? So this is the T-shaped. I think this is what you think of a T. It is a weird T. We have a really narrow base and a really long top. So it's the weird looking T. It's the short but long or short but wide T shaped. And then if you have one more group, adding one more group to the bipyramidal, you have a linear molecular geometry. So xenon trifluoride, you have 5 things, 5 steric group, 5 things. So you have 2 bonding groups, 2 fluorines, and 3 lone pairs. So to this theory, the idea there's 5 things. Those 5 things make it a bipyramidal structure. So that's a bipyramidal geometry. And if you look at the molecular geometry, this is linear. So all 3 atoms are collinear. It's not bent, meaning it's linear, so heart, so xenon, fluorine, fluorine, it's a line, it's not bent like water, it's linear. And this is going to, again, be important later because of molecules being polar or nonpolar. And it turns out this molecule is nonpolar, which we'll talk about maybe later today, maybe not. So, but anyways, bipyramidal structure. And also hybridization. I didn't talk about hybridization for this. Hybridization for this is sp3d. And that's going to come important later. So all bipyramids have sp3d hybridization. Okay. How you guys doing? You look like you're being attentive. Are you following? Any questions so far? Yeah, and that's one of the things. This is why people were so bummed out this theory is wrong, because it makes so much sense. Doesn't this make sense? Aren't you coming here like, yes, I get this. I know geometry. I can do this with ping pong balls and straws and skewers, right? I can make these molecules and then I can know chemistry. And it's wrong. Like, oh. It's mostly right. It's mostly right. And the quantum mechanical model usually fits this. There are a few cases where it doesn't fit. That's why quantum is right and this is wrong. But, all right, so let's go on to 6 things. So sulfur hexafluoride, the stuff we put in our stealth fighters. And now China's got one too. Did you see that? They got a new stealth fighter. So I don't know if they put sulfur hexafluoride in that. Who knows? Maybe they put something different. I don't know. Anyways, back to here, sulfur hexafluoride. So we have 6 things, and 6 things around a center, and it forms an octahedron. So an octahedron so fluorite. Has anyone ever seen fluorite before? Some people think it's a diamond. Diamonds don't have this geometry. Their structure is known as a zinc blend. So I misspelled fluorite. Okay. Where's a fluorite crystal? There we go. There's a better one. This is an octahedron. This is an octahedral geometry. So just like molecules, I was just in a meeting before class and we were talking about fractals. Has anyone ever heard of fractals before? No, you haven't. Okay. It's when small things, there's patterns that happen with small things that can extend to larger things. So like crystal structure patterns can mimic molecular structures, can mimic what mountains look like. So that's one of the ideas behind fractals. So, but this structure here, this is octahedral. And octahedral is the same structure as a cube, actually. So cubic structure is also octahedral structure. So, but we pick one, we call it octahedral. Can I do this? Come on, Apple Pencil, don't fail me now. I wonder if the battery is just dead. It's working. Yeah, okay. So if you have a cube, and then you look at each of the vertices inside the cube, it forms an octahedron. If you can't see that, okay. So I tried to draw a cube. So if you can imagine a cube, so this side, this side, this side, and if you take the vertices, so the 6 vertices of that, if you connect the lines, you get an octahedron. So a cube and an octahedron actually has the same type of geometry. So that's why when you see something like fluorite, you can see them in octahedrons and you can see them in cubes. So I can show you. Pyrite is another one. Oh geez, wrong. Sorry, I was doing that. I like the chive. So if you can look at pyrite. So this is pyrite, this is fool's gold. You can see it as cubes. So it has the cubic structure. You can also see octahedra. So you can, it's the same, it's actually the same structure. Cubic and octahedral. But anyways, so back to VSEPR. So 6 things, 6 groups, 6 electron groups. We have octahedral geometry. So if the 6 things are bonding groups, and when I say bonding groups, I mean not lone pairs. I mean the sulfur and the fluorine are sharing electrons. That's what makes them bonding groups. And then the lone pairs on nitrogen or water, the electrons are not connected to another atom. They're just out there and occupying space. So anyway, sulfur hexafluoride, all groups, 6 groups, all bonding, octahedral electronic geometry, and octahedral molecular geometry. And the hybridization for this is sp3d2. So we'll talk about that later, sp3d2. So now what's different about the octahedral versus the bipyramidal, so the trigonal, at least that's just a trigonal bipyramidal, you have the equator and you have the 3 atoms in the equator, or 3 groups I should say, 3 groups, sites in the equator, have a bond angle of 120 degrees. And then axial, it's 90 degrees. Here, I mean, we kind of draw it with the equator. The equator it's perpendicular. So I'm not super flexible. My bone structure is actually altered because I lift weights so much. Actually, I found that out. So if I look kind of awkward sometimes, it's because of my decades of lifting weights. So the bond angle along the equator is 90 degrees, as is to the equator to the axial. So there is no such thing as an equator or an axial on an octahedra because they're all the same. So in an octahedron, I mean, you can draw it with the equator, but the equator doesn't mean anything because the equatorial position is the same geometrically wise as the same as an axial position. For most cases. So there is something called the Jahn-Teller effect where the axial is skewed, and that happens for copper. That's called the Jahn-Teller effect. But that's a very rare one. So it's mostly just all evenly 90 degrees. So All of them are the same. Doesn't matter where you put the next lone pair. So if you put a lone pair, so now bromine pentafluoride. So bromine pentafluoride, we have a lone pair. So we have 6 groups, 5 bonding, 1 lone pair. So still 6. 6 groups means octahedral geometry, means sp3 dehybridization, which we'll cover later. So same hybridization, same electronic geometry. The molecular geometry, though, is a square pyramid. So this is the Egyptian pyramids. The Egyptian pyramids are square pyramids. Okay, so, and it doesn't really matter which one you chop off. So like here, if you have the fluorine, if you were to say, oh, I'll have this one instead, you still have a square pyramid. It's just on its side. So they're all equivalent. Now, the next thing, though, we're going to go at one more, and we're going to add another lone pair. So we're going to add another lone pair, and we have this very large diffuse area of negative charge. So valence shell electron pair repulsion. So outside, valence shell, outside electron groups repel. We have this really large negative group, and that's the other thing, because when you have a lone pair, it's like a big, huge ball of negative charge, because it doesn't have a nucleus. So if you have a hydrogen atom, here, and you have this big, and you have an electron cloud, the positive center of the hydrogen atom will draw in that electron cloud towards it. If there's no positive center, what happens? Well, the electron is just, because electrons, remember, they're these particles that can be in many different places at once, and they're negatively charged. They can actually repel themselves. So that's, they can have, like, I guess it's not very good to be an electron. You're very negative in a very, colloquial sense too. I'm an electron, and I repel myself because I'm negatively charged, and I can be in many different places at once. I don't even like myself. I want to be as far away from myself as possible. So that's what electrons do. They spread out. Like, okay, well, if I don't have anything to draw me in, I'm just going to fly. I'm just going to make myself huge. And that's what they do. So you have this lone pair. It's still, bound with bromine. And it doesn't, and an electron actually does have its wave function exist for all space in the cosmos, but it mostly hangs out in one spot. So, this cloud is much bigger than a fluorine atom, for instance. So if you put another big diffuse cloud somewhere, where is it going to go? Is it going to go along here, where it would be 90 degrees to each other, or is it going to be up here where it's 120 degrees? It chooses to be along a line to go the 180 degrees, 180 degrees. So if you have, if I have this big negative group, is the other group going to go here, or is it going to go here? It's going to go 180 degrees away rather than 90 degrees. So the extra electron group, actually it's fortunate someone left his or her fruit. Adding one more electron group gives square planar electron geometry. So the xenon tetrafluoride. So xenon tetrafluoride, the electronic geometry is octahedral. There are 6 things. 4 bonding, 2 lone pairs, but 6 things. 6 things mean the electrons are going to be octahedral in shape. It means that the hybridization is sp3d2. Talk about that later. Like I said, sorry if I keep on repeating myself. I'm hoping that this will start to cement in your minds. But then the molecular geometry is square planar, which means that all of these atoms, all 5 atoms actually, including the xenon, are on the same plane, at least the center. I mean, I know that there are spherical balls, but if the centers, the nuclei of these, even the nucleus is kind of spherical as well, but the center-ish of the nuclei, because nuclei are weirdly shaped too, they would all be coplanar. So this is a flat molecule. And there's a standard drug for cancer treatment called cisplatin. That is coplanar. Cisplatin is also what's known as an alkylating agent. An alkylating agent causes DNA strands to cross-link, which is also a mutagen. So one of the more powerful alkylating agents is mustard gas. You guys have heard of mustard gas, haven't you? Mustard gas is not even a gas, it's a liquid. It's a blistering agent. And it's very hard to kill somebody with mustard gas, but you really make their lives miserable. It was invented by Germany in World War I because the U.S. Marines were kicking their butts, and they found out that if they shot soldiers dead, that didn't slow down an advancing army. But if you injured soldiers, it would slow down and advance. So what did they do? They put a bunch of they would put mustard gas down, and they would evacuate their trenches. And then days later, a day or 2 days later, the soldiers would get covered in blisters, and then they had to be treated. They didn't die, but they were covered with blisters, and they had to be treated. It greatly slowed down the Allied advance. So that's an alkylating agent, and alkylating agents also cause cancer. They're mutagenic. And alkylating agents also treat cancer. So stronger versions cause cancer, weaker versions or lower doses treat cancer. So it's interesting the way that drugs work that way. So that's cisplatin, and that has a square planar. That's one of the first chemotherapy drugs that we've been using. So, questions so far? All right, summary. And I will give you this chart. I've decided I will give you this chart on the final. So I know I said I give equation sheets, but I'm also going to give you charts. I'm very much against memorization in this class. So, and I sometimes get students in my office hours, and they'll ask me some things like, "Oh, how am I supposed to know that?" kind of thing. There is actually a lot of memorization in chemistry, and because I mean, you have to, for instance, remember that electron is negatively charged. And sometimes I forget that. I'm like, oh, of course electrons are negatively charged. And protons are positive. I mean, the neutrons are neutral. You know, I mean, everyone knows that. No, not really. But I try to limit the amount of memorization that you should have to do because I want you to focus on the process. So that's why you get many of my charts, many charts and stuff on the test. And that's also why I let you ask questions. Right, if you didn't notice, not too many people have asked me questions, but although last test people asked me what the heat of formation of chlorine was, and it's 0 because it's an element. But I mean, I forgot to put that on there, just because that's the standard state. But how would you know it's a standard state? Which makes sense, you know, kind of thing. Oh, and I still have a student that needed to take the test today. That's why I'm not giving it back. So if you're wondering why, hope you don't. I can give it to you if you really want. We can meet after class. But anyways, so here is a summary, which you do not have to memorize. You will be provided. But in fact, I think I even take this picture, but I chop off the examples. So you can't, because that way you can't go back and figure out the Lewis structures and that. So let's start at the top. So 2 groups. So we have, starting at the top, 2 groups, both bonding. So 2 groups, both bonding. The electronic and molecular structure is linear. Can you guys read that? Raise your hand if you can't read that. So you can read that. Okay, good. So 2 groups, both bonding. Electronic geometry, what the electrons look like, are linear. Molecular geometry is linear. The hybridization is sp. That means an s orbital and a p orbital combine to form 2 sp orbitals, and sp orbitals are linear. And here are some examples. Carbon dioxide. Carbon dioxide has, and let me zoom in. This is a misconception. So carbon dioxide is a linear molecule because you have a central atom and you have 2 groups. I know it's a double bond. The double bond doesn't mean anything. It just means it's bound a little more strongly. I know it's a fuzzy line. This is a double bond. So this carbon sees an oxygen and an oxygen. So my center of my universe is my carbon, and this carbon sees 2 atoms, and it's bonded to it. So that's a bonding group of 2 bonds. So group of 2, 2 bonding, no lone pairs. That's linear geometry. So making sense? All right, so 3 groups. So 3 electron groups. So everything that has 3 electron groups around it that's bonding, non-bonding, it's planar, trigonal planar. So three things, all coplanar. And anything that's the trigonal planar has an sp2 hybridized orbital, which means you have an s orbital and 2 p's. They form a hybrid orbital. I know we haven't talked about this yet. They form the hybrid orbital, which has 3 lobes. So 2 here, 1 here. Now the 3 groups, all bonding. If they're all bonding, then you have planar electronic geometry, planar geometric geometry. So the atoms are all coplanar. So all of them are along the plane, along this same flat plane. And the angle of them is 120 degrees. So especially if they're all the same atom. Now, what if you have 3 things, 2 bonding, 1 non-bonding lone pair? What happens is that you have the electronic geometry is still planar, the hybridization is still sp2, but then you have the molecular geometry is bent. So it's bent here, and the bond angle is a little less than 120 degrees because of that negative charge here is 120 degrees, scoots it in a little bit. So you have a little bit less than 120 degrees, and sulfur dioxide. So the smelly stuff that comes from the volcano, or some of the smelly stuff that comes from the volcano. That stuff here, it has a lone pair and 2 bonding groups. Actually, there's also a resonance structure with this. So these bond are actually the same. At least, well, the double single bond are actually the same blended bond, which is also supported with molecular orbital theory. So that is carried through with molecular orbital theory as well. So all the same, and then you have the bent structure. The bent is it's a V-shaped molecule. So we call that bent. Now, next group, 4 things. So 4 electron groups, and 4 groups, 4 bonding, no lone pairs. So 4 bonding, no lone pairs. The electronic geometry is tetrahedral. So anytime there's 4 groups, it's tetrahedral. And that's an sp3 hybridization. So s orbital and 3 p's hybridize, and it forms a tetrahedron. So all electronic geometries are tetrahedron. If they're all bonding groups, the molecular geometry is also tetrahedral, and the bond angles are the idealized 109.5 degrees of the tetrahedron. And methane is an example of that. So all atoms are the same, all bonding, perfect tetrahedron. So 4 things, 3 bonding, 1 lone pair, still tetrahedral geometry. So we still have electron groups forming a tetrahedron, still sp3 hybridized. And the idea with this lone pair, one of the lone pairs is going to form in that orbital, which we'll show more later. And then the molecular geometry, which is different, is pyramidal. So ammonia has the pyramidal structure there. It looks kind of like, you ever seen those like happy massagers? They look kind of like that. Like, you ever seen that? They have like a center on the ball. Sometimes they got 4 prongs too. Maybe it's like that. But if you have if you've seen that, you have a big ball in the center and you have the balls on the side. And you can take it and like, rub someone's back with it. That's kind of like, that's like the pyramidal structure of these molecules. I'm sorry, this one here. This one there, the ammonia, has that sort of 3-pronged happy ball back massager sort of structure. And if you have 4 things, 2 bonding, 2 lone pair, the structure, so the electronic geometry is still tetrahedral. The molecular geometry is now bent. So you have the V-shaped molecule. Water is like that. Water has 2 lone pairs, 2 bonding groups. So and this is where students get confused. Water here has four groups. 2 electron non-bonding groups and 2 bonding electronic groups. So that's still 4. And I'm including this myself. If you have 4 groups, 1 bonding, 3 lone pairs, the electronic group is still tetrahedral, but the molecular shape is linear. So, but if you have 2 atoms, so like hydrofluoric acid right here, HF, that has one electron bonded groups, but the fluorine, if you look at the fluorine here, it has 3 lone pairs, 1 bonding group. That's still 4. And I'm including this also because sometimes students get confused about what geometries are, and because that's going to become important later when we talk about whether molecules are polar or nonpolar. If there's 2 atoms, it's got to be linear. I mean, that's just Euclidean geometry. 2 points to find the line. So it doesn't matter if it was 2 points. I can give me any 2 points, I can draw a line through it. So just give me any 3 points, I can draw you a plane. So 2 points, 2 atoms will define a line. 2 atoms have linear geometry, but this can kind of help you to see that in terms of where the logic goes in this chart, at least. And for 4 groups, there is that sp3 hybridization. Oh, I didn't mention the bond angles. The idealized tetrahedron has 109.5. If you add 1 or more electron groups, it's going to shrink that bond angle down. For linear, it's 180 degrees. So line, that's the definition of a line. I mean, can you, okay, so if I have my fluorine and my hydrogen, can I move this? What's the bond angle now? What's the bond angle now? It's still 180 degrees. It's still I mean, although I know my arm's not perfectly attached to my heart, but it doesn't matter where I do it. It's still that 180 degrees because that's what a line is. It's 180 degrees. Questions so far? Okay. So 5 groups, 5 electronic groups. If 5 groups are all bonding, you get the bipyramidal structure. Well, any 5 groups has electronic geometry of bipyramidal. If they're all bonding, they have trigonal bipyramidal structure. And the hybridization, which will be covered later, it's sp3d. And that's the reason why I told you, after period 3, you can have the expanded octets. So period 2, so lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, they can only be up to a tetrahedron. So those tend not to form expanded octets, whereas period 3, which includes so sulfur and phosphorus, so phosphorus under nitrogen, sulfur under oxygen, those can have more chlorine under fluorine. That can also have an expanded octet. So period 3 and beyond, because n equals 3 can have that L equals 2, which is the d orbital. But n equals 2 can only have L equals 0 or 1, which is an s and a p orbital. So sp3d hybridization is the bipyramidal geometry. If they're all bonding groups, it's bipyramidal molecular geometry as well. If you have 5 groups, 4 bonding, 1 lone pair, still bipyramidal electronic geometry, still sp3d hybridized. The structure is your seesaw. So think of your best friend in the park playing on the seesaw. There's a seesaw because you have that little V there. And then 5 electron groups, 3 bonding, 2 lone pair. Still bipyramidal electronic geometry because 5 things means bipyramidal. So 3 bonding with the central atom. This is now T-shaped. So also remember, this is with the 5 things. 3 things bonding can also be trigonal pyramidal, like ammonia. That's 3 things. But since the electronic geometry is a bipyramid, these 3 things form the T shape. with the electron groups along the equator, and then you have that long-looking, funny-looking T. So the short but long T, or maybe wide, I should say. Short but wide. Now, then one more group, 5 groups, 2 bonding, 3 lone pair. The electrons all go along the equator, and we get a linear structure. So linear structure there. And then moving on to octahedral. So octahedral geometry here. So 6 things. 6 things. Anytime there's 6 things, 6 electron groups, it's octahedral geometry. So octahedral geometry means sp3d2, the s orbital, 3 p's, and 2 of the d's. Specifically, it's the dx squared minus y squared and the dz squared. And the one up there is the dx squared minus y squared, including the other one. So if you're wondering which orbital actually it bonds to. But, okay, so we have these hybridization orbitals. And so 6 things, all bonding groups. We have octahedral geometry as well. If you add 1 lone pair to that, so still 6 things, 5 bonding, 1 lone pair, still octahedral geometry, electronic geometry. The molecular geometry is square pyramidal. And so just like the Egyptian pyramids. And if you have 1 more lone pair, so 6 things, 4 bonding, 2 lone pairs, we have a square plane. So then all 5 atoms are coplanar. And, I guess up here, TD, so, it didn't show, my pen died. You see how I wrote TD? That's shorthand for tetrahedral. And OH, capital O, little h, is octahedral geometry. So have you ever heard about these, the Platonic solids? Have you ever heard of the Platonic solids before? No, you haven't. Okay, so there's 5 of them. There is a tetrahedron. There is a cube. There is an octahedron. There is an icosahedron and a dodecahedron. So have you ever heard of those before? So those are known as the 5 Platonic solids. And geometry-wise, a octahedron and a cube are the same geometry, and also an icosahedron and a dodecahedron are the same geometry as well, because you can fit a icosahedron inside of a dodecahedron. So that way, so the same geometry, and certain molecules form those structures. So I don't know if do you guys do gaming like dice? Maybe you've seen dice. An 8-sided dice is an octahedron as well, or a 6-sided die is a cube. And a soccer ball is actually a truncated. That's when you chop the tops off of a truncated. Is it an icosahedron or dodecahedron? It's a dodecahedron. So you can chop the edges off those, and there's truncated solids as well. So didn't study that in. Okay. Huh. Okay. But anyways, there's your back to Platonic solids. Huh. So you guys didn't study that in grade school? You didn't? Okay. Oh, sorry. I remember studying that. What's that?
I was just saying probably. I feel like Hawaii is kind of behind on
Oh. But I was a weird kid because I was like developmental in English, but advanced in math, so probably from my ADD, I don't know. So I was in a different class for math. But anyways, maybe it was just for that class. Or maybe I learned in high school, I don't remember. But anyways, where I really learned about it is spectroscopy. So because spectroscopy really deals with symmetry. And these different molecules have different symmetry, which means they have different effects. Their spectra changes, the way they interact with light, and the way that light and matter interacts is very geared upon the symmetry of the molecule. So, and what wavelengths they'll absorb and what their spectra looks like. It's all geometry. But that's above and beyond this class. You'll learn about that if you want to study that later. But anyways, and also, so this chart goes on. Okay, there are molecules that bond with 7, that bond with 8, and so the VSEPR chart goes on. We are not going to, in this class, we're going to stop at 6. So we're not, you can look at other ones, and so bonding with 7 is going to have, just like the bipyramidal, you have so 5 along the equator, and then above and below, and then as you get more and more numbers, the equator just gets bigger, and then the axial stays the same. So, but generally speaking, those molecules tend to be more exotic. You tend not to form those as readily. It's more of a special case scenario, and they also tend to be unstable. So they're hard to make. Unstable means they tend to react and break apart. So just like an unstable couple, like what happens to an unstable couple? They fight and they come somewhere, they fight, and then they leave. So that's an unstable couple. A stable couple is always together. So stable molecule is always together. An unstable molecule is broken apart, or easily broken apart, kind of thing. So, questions so far? All right, we're going to stop here today then. And I will